Mommy doesn't make it like that.
This is a daddy way of making it.
Yeah, she chops everything up.
Well, the nice Jimmy Dean people chop this for me.
Why?
Because I like making breakfast, but I don't always have time.
Why?
Because I have to be at work early to light and heat the earth.
The day begins with a great breakfast. Introducing new Jimmy Dean skillets. Diced potatoes, peppers, onions, and sausage. You just add eggs.
How many of you remember this commercial? I love this commercial. I love it. So one of the main things with this commercial is that we really forget about how powerful the sun is. It comes up and it lights the earth to get us every morning and light the earth and heat the earth, which I think is amazing. One of the things that we're going to talk about today is how sun power and sunscreen is going to be related to the work I'm doing on renewable energy. So sun. So why do we care about the sun power? One is because it is renewable energy. It is also a highly abundant. And what I want to do is I want to absorb that sunlight with special sunscreen. In terms of here, what we want to do is we want to take sunlight and we want to absorb it using these plastics. One of the things we have here is why it's so abundant is because we have 270,000 terawatts of energy is produced by the sun every year, which is 7,000 times the amount the whole entire world energy consumption is. So it's clearly that we have enough energy in the sun, okay? The problem is that we need to develop technologies to take that sunlight into usable energy that in a very cost-effective way. So one way to be able to do this is a solar cell. And a solar cell is basically made of glass, 2 electrodes, and the active layer. The active layer is actually where all the action happens. So it's going to be where you're going to absorb all the light, and we're going to create electrons. And those electrons are going to flow to make power. So it seems pretty simple, right? But what we need to do is we need to be able to have a very good active layer. It needs to be able to absorb a lot amount of the sun. The active layer that we're using at this point is silicon. And if you know silicon is basically what we use in silicon chips, right? And so silicon chips are well known in computers, but it's also used in solar cells. And most of the solar cells that we have now are made of silicon. But there's some drawbacks with silicon. One, it has high cost. So it's high cost in terms of producing it. It also has high temperature to process it. They're heavy and they're bulky. So when you ever put these on your roof, you actually have to have a very sturdy roof. But one great thing about it is that it actually has a high power output. So it actually produces a lot of power. But what I want to do is I want to use plastics as a way to be able to use for the active layer. Why we want to use plastics? Because they're low cost. They have low temperature solution processing. We can actually do roll-to-roll printing. When you don't think about roll-to-roll printing, you think about making newspaper. We can also use the inkjet to print these materials. They lead to lightweight solar cells. They're flexible, but the current problem that we have now is they have low power. And so what we want to do is we want to absorb more of the sunlight so we can actually produce more power. So here are some future plastic solar cell applications. Here you can see that we have lightweight chargers that we can use for charging electronics. One really key thing is actually being able to have solar windows. So in the middle here is a solar window, and you can actually have this as the material on the window to power the whole entire building. One key is to be able to have some transportation. So you have a golf cart, and instead of actually powering that gas cart with gas or whatever, you can have a solar panel on top of that can be able to power that whole entire vehicle. One really key is being able to use it for the military. So we can actually have a solar cell to power a GPS that is implanted onto the wrist of a soldier that can actually be able to tell the location of that soldier. Another key is to be able to have them in electronic textiles. So we can actually make these to be able to power electronic textiles. But one key thing that we need to talk about before we get into the details of this talk is absorbing sunlight. So I need to tell you about what absorbing sunlight is. So if you think about this helmet here, the white portion of this helmet is actually, you see white in this helmet is because that it is reflecting all visible light, okay? The dark edges around that, the black around the edges of this OSU, that's because we're absorbing all of the sunlight. So we're absorbing all of the energy of the rainbow. I mean, all the colors of the rainbow. And then the OSU, the brightest orange, that is because we are absorbing all of the light, all of the sunlight, except the lights that are making up the orange, the brightest orange. That's key because this sunlight that we're bringing in is what we're going to use to make power. So here is a typical solar spectrum in red. This is a typical solar spectrum for the sun on a normal day. In green is a typical plastic that actually been used as the active layer in a polymer. As you can see, that polymer doesn't do a very good job of absorbing the light. And so what we want to do is we want to absorb at longer wavelengths. We want to absorb more of the sunlight that we can then direct it to power. So what do we want to do? We want to make basically black plastic. Because black plastic means that we're absorbing all wavelength, right? We want to convert that into electricity that we can then make low cost, lightweight, flexible solar cells that we can actually make commercially available to everyone. So the materials that we're interested in using for the black polymer is Eumelanin. Eumelanin is a class of naturally occurring pigments that is found in hair, skin, and in the brain of living things. The lack of a melanin is actually why this peacock here is white, because again, it is reflecting the light. It doesn't have any eumelanin to absorb that light. There's two types of eumelanin. One is eumelanin, and it's actually the black version. And there's also phyomelanin, which is the red, the yellow-red version, and it's responsible for red hair and freckles. And the black-brown version is responsible for dark color, skin, and eyes, and hair. So we're interested in using the Eumelanin because we know that it's going to be able to absorb most of the sunlight. Here is a nice picture of, I don't know if you can say it's nice or not, but this is a picture of Eumelanin. It's actually the ink sac of cuttlefish. And Eumelanin in itself is actually a black insoluble polymer. I mean, what we want to do is we want to make it soluble so we can make devices. Here, also, this ink sac of the cuttlefish is actually used to make black paella. So if anyone makes black paella, this is where we get black paella from. So also the concentration of Eumelanin is important because it tells us how much light we're going to absorb. So if you look at these eyelids here, we're going from blue eyes to dark brown eyes. You can see the dark brown eyes actually has more Eumelanin, and that's the Eumelanin that we are interested in having. Finally, in my group, I'm interested in synthesizing black polymers, Eumelanin polymers, that can be used to absorb all sunlight that we can then make low-cost, flexible, lightweight polymer solar cells that we can then use in a variety of applications, but also we're interested in it being accessible and affordable to worldwide. But one key take-home that I want you to get is that chemistry is awesome, okay? That this work is actually being done at OSU in my lab by graduate students and undergrads. Most of this work is being done by very, very talented undergrads. And if you look at these materials, we have this reaction here where we actually dried it out and it formed a polymer that looks like copper, right? If you take this polymer and dissolve it up in a solvent and you put a black light on it, you can see that it actually fluoresces a different color, okay? But what's one key I didn't tell you about is that these materials are conductive. These are conductive plastics that absorb all light and convert to electricity. And that's the key point I want you to know about my lab. And with that, I say thank you.